Let's start the lesson. Uh, Everything working. Dear students, presented here. Let me welcome on the online meeting our colleague on Technical University in Graz, an automotive institute department, electrical power engineering, no. Institute of Automotive Engineering, yeah, Associated Professor Mario Hirz. Uh, he has prepared the lecture about the electric mobility and about the basis ideas how to go from standard driving systems which we know today to electric drives and propulsion systems. And okay, I give him the speech and presentation, and welcome Mario, and you can start with the presentation.
Yes, good morning. Thank you very much, Peter. It's a pleasure for me to be here online today in this lecture. And I will talk about propulsion technologies. At first, I want to introduce myself. So I'm associate professor at the Institute of Automotive Engineering at Graz University of Technology. I hold a PhD from internal combustion engine. So initially, I come from the internal combustion engine side, but then I moved to the Institute of Automotive Engineering, and my research topics include alternative propulsion systems, future mobility, and sustainable transportation. Besides my job here at Graz University of Technology, I'm also researcher and a lecturer at different universities worldwide in United States, also in China and Asia. And I'm very happy to be here with you in Czech Republic today. Yeah, we also have some international cooperation. So here I'm head of a scientific double degree program and of scientific courses in continuous education. Now let's jump into the topic of today. When we look at the automotive industry, we can read a lot in the newspapers and we hear a lot about this transition. And when we look at the reasons or the technical background for transition, we have at first as a very important impact legislative boundary conditions to reduce emissions. This is targeting on propulsion systems, and this is the main focus of my lecture today. Besides that, we have digitalization and automation. So automated functions, autonomous driving cars, for example. I will not touch that today. And the third factor is new mobility concepts. So new ways how to do transportation, people and goods transportation. And this changes a lot in automotive business. But today, I will focus on the propulsion systems. And this change of propulsion systems is driven by legislation. And I would like to start with this topic. When we look at exhaust emission legislation, we can distinguish between the so-called harmful exhaust emissions. These are emissions that are bad for the health, bad for the environment in general. And then we have the greenhouse gas emissions, CO2. CO2 is not, in fact, harmful for the health, so we breathe it. So it's a part of the biocycle, but it leads to global warming, and therefore it's also restricted. Perhaps some words in the beginning about the harmful exhaust emissions. Here we have hydrocarbons, we have carbon monoxides, we have nitrooxygen, and we have particulate emissions. These emissions are initially targeting to combustion engines because combustion engines produce such emissions. But in the latest European legislation, they also target all cars, so also electric cars. But of course, electric cars have no hydrocarbons, right? They have no exhaust, they have no particulate, no carbon monoxide or nitrooxygen. But electric cars also have particulate emissions, tire wear, and brake emissions. And this is covered with the new legislation, the Euro 7, this time. Anyway, these emissions, these types of harmful emissions, are measured in standardized test cycles. So I have here the worldwide light vehicle test procedure, and RDE means real driving emissions. So there are different test cycles where the vehicles are measured. These test cycles are standardized and the emission limits are defined. And what we see here on the right side is just one example of nitrooxygen emission reduction. And we see that for all markets worldwide, there is a significant reduction when we look at the timeline from about 1990 to today. So there is a significant reduction. Is it in Europe? Is it in United States or in Asian markets? The second type of emission where I will mainly focus today are the greenhouse gas emissions, so the CO2 emissions. And with the greenhouse gas emissions, it's a little bit more complex because they are produced in case that we use hydrocarbons as energy carrier. So when we have, for example, gasoline fuel or diesel fuel, these are more or less hydrocarbons. So we have HX, CY, so a mixture of hydrocarbons, right? And in the combustion engine, we burn them. So we burn them with oxygen, and this results in a, of course, multi-step process. It results in water plus CO2, plus I put it in brackets, some other emissions which are related to this here, right? So these harmful emissions. And just to be correct in the chemical way, I add here mass factors A, B, C, D. But what we can learn out of that is that a specific amount of fuel, for example, diesel or gasoline, results in a certain amount of CO2. And this is the way that we have in the chemical process when using a hydrocarbon as a fuel. In that way, we do not have possibility to reduce the CO2 impact in case that we have gasoline or diesel fuel. We just can reduce the fuel consumption. Another way is, and this is the new idea, it's the electrification of mobility. So it's shown here. When we use another energy carrier than hydrocarbons, of course, we can reduce the CO2 impact. Or we can use hydrogen as a fuel. In hydrogen, we do not have carbon inside. So here we also do not produce carbon dioxide. And another option I will show you later is to use synthetic fuels. In the synthetic fuel, the idea is to take CO2 from the atmosphere to produce a fuel so that we have a closed cycle when we use this synthetic fuel as an energy carrier. The vision of the European Commission is to have some kind of carbon neutral continent in 2050, which is a really challenge, so a big target. Anyway, and the European Commission also defines intermediate targets. So, for example, 50% reduction of CO2 in 2030. How does this look like? When we look at this diagram, we see here the emitted CO2 emissions in Europe over the timeline, and in 2090 we have the baseline. So here it's in 1990, we have the baseline 100%, and we look at the progression over time. We see that many businesses could reduce their CO2 impact. So agricultural, buildings, power generation, industry, waste management. But the transport sector had a plus of 29%, so no reduction. And this is the reason why the European Commission is pushing so much the transportation industry to reduce the CO2 impact. Because the target, remember, it should be reduced 50% in 2030. So the transport sector must come down somewhere here, it's 50%, right? So we should come down to that level. And this is a big, big challenge. Okay, let's have a look at the impact of the transportation sector. How much CO2 is produced by the transportation sector? And when we look at this diagram, we see on a worldwide consideration that about 23% of all fossil-based CO2 emission come from the transport sector. This is worldwide. At the EU, so in Europe, it's about even 28%. So because we have more traffic in relation worldwide than worldwide. The other branches are agriculture, industry, power generation, and so on. And when we look at the transportation sector, we have about 5% railway, about 11% aviation, 11% ships, so naval industry, and about three quarters is the road transport. And in the road transport, a little bit less than half is the heavy industry, so the trucks and buses, and a little bit more than half is the cars and motorcycles. In that way, worldwide consideration, when we multiplicate the 23% with the 74, we have about 17% of all CO2 emission come from road transportation, and here a little bit more than the half from cars and less than the half from commercial transport. The politics now applies measures to reduce the CO2 impact, and this is done by so-called fleet emission targets. What does it mean? This means that the fleet of cars which are sold in a year as new cars have to be in average below a certain threshold value. And as you see, for all markets worldwide, we again have a decreasing trend here. So even United States or China have this, but the most strict regulation this time we have in Europe with 95 gram CO2 per kilometer driven. What does it mean? 95 grams CO2 per kilometer means about 4.1 liter fuel consumption gasoline or 3.6 liter fuel consumption diesel fuel per 100 kilometer. How this is calculated, I'll show you later. It's just a simple factor used here. For 2030, we have the 59 grams target, and we see that these values are really small. So 2.6, 2.3 liter per 100 kilometer is not easy to reach with an average car. And this means we need electrification. So a certain share of cars have to be electrified to reach the target. And for 2035, it's discussed in Europe to even have zero CO2. So zero CO2 means battery electric vehicles, BEV, battery electric vehicles. We can use hydrogen as a fuel, right? Because we have zero CO2, or, and this is in discussion today, so I put it in brackets, we can use e-fuels, which also show a neutral balance, but this is in political discussion today. I will show you later how does it work. Yeah, if the car manufacturer cannot reach these targets, the European Commission requires a fee. So they have to pay penalty for that. And This is a lot of money. So the legislation says it's 95 euro per gram CO2 per car sold a year. I just want to play a little bit with numbers to give you an idea how much does this is. So let's go here. For example, let's look at Volkswagen Group. So they sell about, it's just a number, so it depends a bit, but let's say about 3 million cars. They sell per year in Europe, right? So if Volkswagen would be only 5 grams above, so let's assume they do not reach 100, they do not reach 95 grams per kilometer, as it is prescribed here, but they have 100. So they're a little bit above of this target. This would mean that if we have 5 grams CO2 multiplied with 95 euro per gram, multiplied, so per car sold with 3 million cars, this results in about 1.5 billion euro. I just want to show you with this number, it's expensive for the car manufacturer if they do not reach the target. They have to pay a penalty for that. Yeah, there are some specific politics, regulations. There was a phasing in until 2023, but this is gone in the meantime. Pooling is allowed. That means that Volkswagen Group is considered. So that includes Skoda, Volkswagen, Audi, Porsche, and the average fuel consumption is counted. So that's one of the reasons why Audi and Porsche can sell cars with combustion engine with higher fuel consumption. On the other hand, Volkswagen, Skoda, and others have to sell cars with lower fuel consumption so that to reach in average the target. And there are some reliefs for small manufacturers like Ferrari here. What are now the strategies of the car manufacturer? How do they react? On the short term, so let's say for the next 3 years about, they optimize combustion engines to reduce the fuel consumption. They build smaller combustion engines because smaller combustion engines have a lower fuel consumption. For example, in the meantime, you can buy big cars with small engines. Mercedes S-Class, a luxury car, is available with 4-cylinder engine even. And a main step is electrification. When we look at electrification, we have the HF, so the hybrid electric vehicles. We have the PHF, the plug-in hybrid electric vehicles. These are hybrid electric vehicles where the battery can be charged on the grid, so you can plug in. And we have battery electric vehicles. These are the main strategies of the car manufacturer, so that the total fleet of their cars in average can reach this 95 gram target. On the long term, so when we look 2030 and beyond, there will be a significant move to electric cars because zero CO2 will probably be the most efficient way to use electric cars. I will show you later a diagram for that. But we have alternatives. We also can use hydrogen-driven vehicles, and we can use synthetic fuels if the politics allows this, so if the legislation allows this. I will treat all 3 technologies in my presentation today. Okay, so far to the legislative boundary conditions in Europe. As next, I would like to look into propulsion technologies. And before I start with that, I would like to talk about some basics. So on this slide, we see the driving resistances of a car. So it's very basics. You know that from physics, I guess. We have the braking force. I come to that later when we brake the car. We have the rolling resistance as a function of the rolling resistance factor. and the mass of the car. We have the air drag as function of the size of the car, the aerodynamic factor, and the speed squared. We have the climbing resistance when we drive uphill, and we have the acceleration resistance when we accelerate the car. And when we look at these resistances, some of them can be recovered during braking. So when we brake the car, we have the possibility to recover some of that energy in case that we have electric drive. I have here an example. So this is a simulation of the driving power demand when we drive a standard car uphill acceleration. We have here the rolling resistance. We have the air drag, the inclination resistance for uphill driving, and the acceleration resistance when we accelerate. And in case that we have a hybrid or an electric car, we can do electric braking. And this is called recuperation. In this recuperation, the electric motor is operated as generator. It produces electricity, and this can be stored in the battery. This significantly increases efficiency. So this is one reason why hybrid cars have typically a lower fuel consumption than cars with combustion engine only. What happens with the energy in case of combustion engines only? The brakes dissipate the energy to heat to the environment. So it's not used anymore. It just heats the environment because of the friction brakes. But in case of electrically powertrain components, electric motor, it's switched as generator and battery, we can recover that energy. This has an important influencing factor on the efficiency. Here, on this slide, I just have on a nutshell general characteristics of the different drivetrain technologies. So I start with conventional drive, it's combustion engine. It's established, it's low cost. We have very quick fuel filling at the gas station. There is some potential for further improvement. I come to that in a minute. On the other hand, we have thermodynamically bad efficiency. So here we have the so-called Carnot process, which is the theoretically perfect process of a combustion engine. And the Carnot process efficiency, so this theoretic efficiency is a function of the temperature in the combustion engine. So the high temperature, so the high temperature minus the low temperature. And these temperatures are limited by physics. So we have as a high temperature about 2300 degrees, and we cannot increase the temperature because of the material. The piston would melt, for example. And in the low temperature, we have the ambient temperature for aspiration. So today, perhaps 0 degrees or 5 degrees, something like that. In summer, 20 or even more degrees. And due to that physical limitation, the Carnot process is about maximum 75%. So this is the theoretical process. The real efficiency, when we consider we have different types of losses in the combustion engine. We have mechanical friction, we have combustion losses, we have blow-by gases, we have scavenge losses, thermal losses, so a number of losses. So the real efficiency of combustion engine, when we calculate the maximum, is about 50% maximum. And I will show you later that in combustion engines of cars, this is even lower. So it's about 43-45% for diesel and about 35% for gasoline engines. So we have a relatively bad efficiency in combustion engines. What's the potential? there is some potential, and I'm often asked this question: how much can we improve combustion engine? And due to that, because I was asked so often, I had a master student. I asked a master student to do simulation. And he simulated the best combustion engine in the world. So he considered all technologies that could lead to an improvement of efficiency, even technologies which are not on mass production scale, which just research. So we had laser ignition, variable combustion, variable compression, valve timing. We had isolation of the engine with ceramics and so on. So all these ideas. And we could reduce the fuel consumption of a car about 20%. But that was then the physical limit. So there was not more potential possible. And just to give you a number, these cars we used as a basis, a modern car with a fuel consumption of about 4.5 liter per 100 kilometer, which is pretty good. We could reduce to about 3.5 liter. But as you see, when we go back here, we are far away. With 3.5 liter, we do not reach the emission targets, right? So combustion engines are in that way some kind of limited technology that will not be able to reach zero CO2 emissions. In addition, we have the local exhaust emissions, so I talked about that, and today the direct dependency on crude oil. What about electric drives? Electric drives are much more efficient. I will show you later that we have a total efficiency, so in the range of about, let's say, 65 to 75% in total. That means this includes the charging losses, discharging losses of the battery, the electric motor, the gearbox, everything included. And with that, we have a significant higher efficiency potential than combustion engines. We have no exhaust emissions, and it's a quiet technology and high driving comfort. The challenges with electric cars is the complexity of the battery system. I will show you later that the battery system is the most expensive part in an electric car. It requires high effort for production, and this is a challenge here also in terms of CO2 emission. We have shorter driving distances, longer charging times, and as a very important factor, the environmental friendliness depends on technology of electric power generation. So when we charge the electric car with water power, hydropower, or solar energy, we have a very low CO2 impact. When we charge the car with coal power, we have a high CO2 impact. So it depends on how electricity is produced. Finally, the hybrids. The hybrids are a smart combination of electric drive and combustion engine. As I mentioned before, a good efficiency is possible. We have no driving range limitation, and there are some specific test procedures defined in legislation for plug-in hybrids. On the other hand, it's relatively complex, and the CO2 reduction potential is significantly influenced by how the car is used. In city traffic, the reduction potential is higher. When we only drive on highway with constant speed, there is nearly no CO2 reduction potential for hybrids. Yeah, I have here just on one slide a short overview of the different technologies. Today I do not have enough time to go deep into that, but just to point out, when we look at hybrid drivetrain configurations, we have different types. We have the serial hybrid, we have the parallel hybrids in different configurations, the power split or combined hybrid. So just a short introduction. In the serial hybrid, the combustion engine drives the electric generator, produces electricity, and this then drives the car. The car is driven by electric motor only. In the parallel hybrid, combustion engine plus electric motor drive the car. And we have a certain flexibility to operate combustion engine, electric motor, or both. In the power split, it's the Toyota system, more or less. So Toyota has introduced that, very successful with the Prius, but in the meantime, they have it in different models. Here, we have a planetary gearbox that can switch very quickly between input and output. So from input from combustion engine or from electric motors. The advantage of this system is that it can very quickly vary the different energy sources for driving the car. Besides of these different architectures, we also have different levels of hybridization. This means how large is the battery, respectively, how large is the electric motor in the system. And here we have so-called mild hybrids with small electric power, just about 5 to 15 kilowatt. We have the so-called full hybrid with considerable electric power, 50 kilowatt or even more, and a small battery. And we have the plug-in hybrid where the battery is larger, 10 kilowatt hour or even more, and can be charged at the grid. The CO2 reduction potential depends a lot on the different architectures. So if it is a mild hybrid, full hybrid, or plug-in hybrid, it depends on the configuration of the powertrain, and it depends on the user behavior. So here, this means how the car is driven. On the electric side, when we look at battery electric drivetrains, we have the energy storage. So it's typically a 400 watt or 800 watt system, the battery system. We have electric motors. As electric motors, we typically use permanent magnet synchronous machines or induction machines, so both is used. And these are typically three-phase alternating current machines. In that way, we need a power electronics that converts the direct current, right, into the three-phase alternating current. And this is a very specific high-performance part, the so-called inverter. I think you know how it works. You are electrical engineers. In addition, we have a gearbox. This is mainly a constant gear ratio, so not shiftable gearbox. Just in some sports cars, we have shiftable gearbox. And then we have the final drive to the wheels. Let's compare combustion engine and electric motors. So there are very different characteristics. On the upper side, I have here a simplified diagram of a combustion engine. And we see we have here engine power and engine torque that is delivered between an idle speed and a maximum speed range. And the idle speed is typically about 800 to 1000 RPM. The maximum speed range is typically about 5000, 6000. In that range, depends on the combustion engine. But anyway, because of this limited speed range, we need a gearbox, right? So in a car with combustion engine, we always need to shift gears to be able to drive very slowly, but also fast on the highway. In addition, we need a clutch system here to start driving. Why? Because at idle speed, we have a certain rotation of the crankshaft, but the wheels stand still when we stop, when we stand still with the car. And to start driving, we need some friction mechanism that overbridges that speed difference. Every time when we operate the clutch, we have losses. This is for starting driving, but also when shifting a gear. This is very different with the electric motor. The electric motor, as you know, as electrical engineers, delivers high torque at zero speed. This here is a simplified diagram, but we see we have here a high torque range up to a so-called field weakening point, And then in the field weakening area, the torque is reduced. The function depends a bit on the design of the electric motor. But we have a very high speed here. So this example is the motor of the electric Volkswagen Golf. It's a little bit older design, but we have here up to more than 20,000 RPM. So it depends on design of electric motor. We have a wide speed range. We have torque at 0 speed. In that way, we don't need a gearbox and we don't need a clutch. So this reduces the losses on the basics of operation. In addition, we can use that as a motor and we can use it as a generator for recuperation during braking. Let's have a look at the efficiency. Here you see a typical combustion engine where we have an optimal efficiency of this combustion engine for cars of 35% in this area. At lower speed and load, the efficiency drops down. So here we just have 22, 25%. One problem that we have with combustion engine is that in daily operation, the engine is driven in this field here where we do not have the best efficiency. So as you see here, we have 27, we have 30%. We cannot reach the best efficiency range. And this is a pity. This is a disadvantage of the combustion engine that at first the efficiency is relatively low, and at second, we even cannot operate the combustion engine in daily driving so well in the good efficiency range. It's a big challenge here. The electric motor, it's here an example of a permanent magnet synchronous motor. It reaches 0.9 or even not more in a large area of the map, as you see here. So the drop down of efficiency is much smaller and the basic efficiency is much better. So 90%, even 95%, some electric motors. Of course, we have to consider also the battery losses and the inverter losses, but they are also relatively small, so that the total powertrain efficiency of electric drives is much better than those of combustion engine. I just write it down. Real efficiency or real driving efficiency. I will call it different. Just give me a second. So real driving efficiency of combustion engine we are here in the range of about 25 to 35% in real driving. The diesels are better than the gasoline. In the electric real driving efficiency of the complete powertrain, we can reach about 65 to 75 or even more percent. So it's about 2 to 3 times better than with combustion engines. Another aspect when we compare combustion engine and electric drive is the mechanical complexity. So in combustion engine drive, we have a high number of mechanical components. So about, let's say, 1,200 to 1,500 parts in the drivetrain. This includes the combustion engine with all the components, the crankshaft, the piston, conrod, valve train, oil pump, housings, and so on. It includes the gearbox with the bearings, the gear wheels, the shafts, the fuel system, and the exhaust system. So a high number of mechanical parts. For the battery electric car, we have about, it also depends on the complexity, 300 to 500 parts. So significantly lower number of parts, which reduces mechanical complexity. We just have electric motor with inverter, a simple gearbox, the battery system, the charging system. But, and I will come to that later, the battery is a high complex component here. I will show you later. Perhaps another comparison about the costs. This slide shows a study that was made by a colleague of mine at TU München, Mr. König. He is a PhD student of Professor Lienkamp. And he has analyzed the production costs of cars. So it's only production costs. And we see that in 2020, it was a compact SUV, so in the size of a Volkswagen Tiguan. The production cost of a standard car is about 14,000 euro. The production cost of a car of the same size, electric, it's about 50% higher, mainly because of the battery. So this is the most effort and the most expensive part. I will show you also later the CO2 impact. Then he made an estimation. So how could this look like in 2030? Where we have a higher volume of battery production, so some kind of effects of scale, which will reduce the battery cost to about the half, right, in 2030. So the combustion engine driven car will be a bit more expensive because of more complex technology for exhaust emission reduction, so that there is a difference of about 10%. Something like that remains in 2030. This is only production costs. So of course we have other costs like maintenance, service, energy costs, and so on, which makes battery electric vehicles very competitive in the near future. Yeah, just to show you this so expensive and complex battery system, this is an example of the Porsche Taycan, a luxury sports car. Here we have a battery of about 94 kilowatt hour energy storage capacity. It's an 800 volt system. We have here 33 modules with 12 cells. I just want to show you the complexity. So we have here the modules with the cells. We have the electric connection, high voltage connection. We have a battery management system, a very complex control system of the battery. And you see here, we have extensive protection. This is one disadvantage of the lithium-ion battery. They burn very well in case of an accident, for example. And therefore, we need massive protection. So these are aluminum beams. Also here in between, we have underbody protection from the lower side. We have different covers. This is the cooling system here visualized. So it's a complex, very expensive system that is represented in such an automotive battery. Regarding battery systems manufacturing, we have another situation that is important, namely the supply of battery cells. About 50 to 60% of the price of such a battery is only the cells. So these are the cells which are here in the modules, and they are very expensive to produce. So more than 50% of the battery is only the cells. And when we look at the supplier companies that are able to deliver automotive battery cells, we see there is a small number of them. So it's the largest one is CATL, a Chinese company with more than 25% market share. LG, Korean, with also about 25% market share. So these two have 50% market share. Then there's Panasonic, Japanese, Samsung, Korean SK, Korean BYD, Chinese, and some others. And when we look at this, we have here 5 or 6 manufacturers which have more than 80% of market share. And what's also visible, all these companies are Asian companies. So we do not have European companies for battery production. And this is a very bad situation. So we have to import this know-how to Europe. In the meantime, these manufacturers also have cell production in Europe, but most of the cells are imported from Asian countries. So this has an economic impact. Let's look at the CO2 emissions. I want to compare the different technologies in terms of their CO2 emission impact. And here we have to distinguish between 2 types of CO2 emission. The so-called well-to-tank emission and the tank-to-wheel emissions. How does it look like? When we have a car with combustion engine, so here on the upper line, we have tank-to-wheel emissions because we drive the car and we burn the fuel. I have shown you in the introduction how does it work, where does it come from. So when we burn hydrocarbons, we have a CO2 impact. In addition to that, we have to consider the different steps of production of the fuel, right? So we have the production of crude oil, we have the transport, we have refining, and the transport to the gas station. This is the so-called well-to-tank emissions. Just to give you an average, this well-to-tank emission for gasoline and diesel are about 15 to 20% of the tank-to-wheel emission. So this is the effort for production of fuel. In case of electric car, we have 0 CO2 tank-to-wheel. That's clear because electric car has no exhaust, right? But we have well-to-tank emission, and this is influenced on how the electricity is produced. I will come to that more detailed on the next slide. When we look at different propulsion technologies, we have very different behavior. What you see here is a comparison of mid-size cars. So it was a BMW 3 Series car that was simulated with different propulsion systems. And when we look at the gasoline, for example, and the diesel, we have a certain tank-to-wheel emission. So this is from burning the fuel. And we have a certain amount of well-to-tank for provision of fuel. The gasoline car has about 6.5 liter fuel consumption per 100 kilometer. The diesel has a less, about 5.5, so a lower tank-to-wheel emission. For biofuels, so when we have here biofuels, we have the situation that in the production of fuel, the plants take out CO2 from the atmosphere. This is in the course of the photosynthesis process, right? This is, for example, for ethanol, but it's the same for rhapsode, so biodiesel fuel. We have here this minus CO2 because the plants take the CO2 out of the atmosphere during the cultivation, during the grow, because of the photosynthesis. Then we can harvest the plants and then we can produce a fuel. There are different chemical processes, estering processes to produce the fuel of the plants. And then we can fill it into the tank and then we have about the same tank-to-wheel emission as gasoline or diesel. But the sum here is very small because we have this negative impact from the plants, right? In that way, biofuels have a very low CO2 impact. Then we have natural gas. Here in this example, compressed natural gas. There is a certain reduction in comparison to the gasoline because natural gas is mainly CH4, so it's methane, where we have a relatively large share of hydrogen and less carbon than in gasoline fuel. We have different hybrids here. I do not go into detail too much. They increase the efficiency, so they reduce the fuel consumption to higher efficiency. And then we have different electric car mixes. Here, it's an electric powertrain, but charged with different electric energy. For example, when we take the European mix, it's about the electric energy in Europe has a CO2 impact of about 300 gram CO2 per kilowatt hour. It results in about 100, a little bit less than 100 grams per kilometer. When we charge the car in the German average mix, it's about 400 grams CO2 per kilowatt hour. It is higher, you see. Or when we take the Austrian mix, in Austria we have a high share of hydropower, so a lower, or Ökostrom means only water, wind, and solar energy. We have a very low CO2 impact. I will come to that point much more detailed on the next slides. Here, I want to explain that electricity impact from CO2 impact from electricity production. So when we produce electricity from coal power, we have about 1,000 grams per kilowatt hour. When we use oil, 700, natural gas, about 450. Looking at so-called renewable energy sources, is it solar energy, is it wood chips, biogas, wind, or hydro, it's much lower. Why is it not zero? These values include the life cycle CO2 emissions, so also the manufacturing of the solar cells or the manufacturing of the hydropower plants and the servicing of the hydropower plants. But we see it's significantly lower. Also, a very low CO2 impact has nuclear power, but not considered in this diagram is the costs of nuclear power. It's very expensive, and the risk of nuclear power accidents, so supergowers or if something breaks down, and not the effort for nuclear waste management. It's only the CO2 emission, but we see the CO2 emission are very low. When we look at the different impacts in different regions, we see here two dimensions. We see at the one, the CO2 impact in grams per kilowatt hour electricity produced in different countries. And we see here how much electricity is produced in that countries. In China, for example, and this is 2 years ago, this diagram, so China is even moving higher here to higher values. We have a very high amount of electricity produced, and we have a high CO2 impact because of coal power. European 27 are here at about 300, and then I have some countries here. Let me see, I don't have Czech Republic. I have Germany here. We see France is very low in their impact because they have 75% nuclear power. Norway is very low. They have 100% hydropower. Nearly 100%, so very low. On the other hand, India, for example, is very high. Poland is very high because they have coal power plants. And what I want to show you is just the information about real-time data. So there are different sources available. I would like to share that on the screen. Let me see if it works. I just want to start my browser. Give me a second. Here, it works. So I have this link in the slide. I change my screen. Give me a second. So can you see my browser screen? Yeah.
Okay.
And it is this electricity maps link. And when we look at that, we see in real time the electricity mix. So when I go to Czech Republic, for example, I see here we have biomass, we have hydropower, we have nuclear power, and we have coal power. So in total, we have 600 grams per kilowatt hour in Czech Republic today. In Austria, we have 365 with different power sources. In France, we see high share of nuclear power and so on. So if you are interested in seeing the electricity mix in Poland, 850 with a high share of coal power, there are several countries worldwide where you can get the data of electricity production of today. They also provide annual data. So when we look at the annual average numbers and other ones. Okay, at the end, I just wanted to show you that how electricity is produced has a big impact on the sustainability of electric cars. Let's do an example. I will just do a simple calculation here to compare a, let's say, diesel car or gasoline car with an electric car. And I want to do a calculation. So I start with, let's say, a diesel car. We assume a fuel consumption, just take a value, 5 liter per 100 kilometer, right? And out of that, we can calculate the tank to wheel emissions. So I just jump back to show you. So this part here, we can calculate by a factor. So the tank to wheel emissions equal to 5 liter per 100 kilometer multiplied with a factor, and the factor is 26.2. For gasoline, it's a little bit smaller factor because the gasoline holds less carbon inside. So I calculate 5 multiplied with 26.2. It's 131 gram per kilometer. In addition to that, we have to consider the well to tank emission. And I just estimate that. I go back to my diagram. So it's this part here, right? And I estimate that with about 15%. So this means multiplied with 0.15, it's about 20 grams per kilometer. So that in sum, well to wheel, we have in total 151 grams per kilometer when driving a diesel car with a fuel consumption of 5 liter per 100 kilometer. For a battery electric vehicle, at first we have to assume an energy consumption. And just to take an average value, so it depends on the size of the car, on the quality of the car, so the efficiency. We can assume, including charging losses for simple calculation, let's take about 20 kilowatt hours per 100 kilometer energy consumption. And now we can calculate the electric impact. So for example, in Czech Republic, we had today at the electricity map. I just go into the internet. Let me see. We had it before. So we have about 600 grams CO2 per kilowatt hour, right? This is the electricity mix in Czech Republic. And out of that, we can calculate 20 multiplied with 600 and multiplied, so divided by 100 because we calculated in kilometer. So this is 120 gram CO2 per kilometer. If we would drive the car in Austria, so in Austria, I just look at the electricity map. We have 300 grams per kilowatt hour. So this would lead to the half. It's about 60, right? Or if we would drive it in Norway, we have 25 grams per kilowatt hour. So very low energy. And when we calculate that, it's only 5 grams per kilowatt hour, right? So with this, it's just a little bit playing with numbers, but I want to show you that the technology of electricity production, of course, influences a lot the CO2 impact of an electric car. So when you charge it at solar power, water power, you have a very low CO2 impact. Did you understand? Do you have some questions to that example?
It's okay, but it's only, let's say, production during the using the car, not manufacturing.
Yes. Absolutely right. And about manufacturing, I will talk in my next chapter. So thank you very much for that input. Okay, this is the next chapter. What's about the life cycle consideration? Life cycle consideration means we also consider manufacturing and recycling. And this life cycle assessment is a standardized process. So there are ISO standards for that. And the standardized process include the complete consideration of the technology. So in the beginning, we have energy and natural resources. This includes material production, so extraction of raw materials, processing of the different materials, refining, transportation of all materials that we use in cars, steel, aluminum, plastics, copper, and so on. Then it includes vehicle manufacturing, so where the modules are manufactured, the vehicle is assembled, production processes, logistics. These two, this is the production of the car, right? So these two factors. Then we have the usage of the car with the well to tank and tank to wheel emissions. This is exactly that what I calculated before. We have the maintenance, we have the user behavior. So here we have the use of the car. And at the end, we have the end of life, recycling, materials extraction, thermal usage of materials. All that is included here with the end of life. And all these three components, production, usage, and end of life, is considered, and I will show you some results on the next slide. We can calculate here different parameters, energy demand, water demand, and so on, but I did it with the CO2 equivalent emissions because they are most popular, most important today. Let's have a look at the different technologies. So when we do such a production comparison, so only the production, we see that cars with internal combustion engine here as 100% set, and electric cars, start with them, have about 50 to 100% higher CO2 impact in production. The vehicle is nearly the same. There is not much difference. There is the electric powertrain, of course, electric motor, inverter, but the most impact has the battery, with about 50% is the battery. In that way, this range here is indicated because it depends on the size of the battery. When we have a smaller battery, the impact is lower. When we have a large battery, the impact is higher. For hybrid cars, it is much dependent on the battery size here. So for mild hybrids or hybrids with very small battery, it's nearly the same as with combustion engine cars. But for plug-in hybrids, we have a larger battery, 10 kilowatt hour, 15, even more kilowatt hour, so that the CO2 impact of production can be about 50% higher than those of a standard car. This is just the first estimation of that impact. We have done that much more detailed, and I would like to show you some results here. So we have analyzed an electric car. It was the Volkswagen ID.3, where we have very detailed made a production. So this is only production of this car. We analyzed the bodywork, exterior, interior, electrics, chassis, and powertrain, including battery. And we see that in total, I just write it down here, we have about 14 tons CO2 in the production of this car, with about 50% only the battery. Then we have the bodywork, so it's the steel. We have the electric powertrain with the copper and all the components, the interior, the other electrics, and so on. But about 50% is only the battery. And when we look at the materials that are used here, we have about 30%, a little bit less, 28% is only the battery cells. Then we have steel, we have electrics for high voltage and low voltage, aluminum, and others. Why is the battery so important for the CO2 footprint of production? I have it here on the next slide. You see the battery here with the different components and the cell modules, the battery cells. And when we look at the shares of CO2 emissions in the production of a battery, we have about 50% electric energy. So this is a main factor. Then we have materials, the cathode material, the anode material. We have the housing, typically aluminum, electronics. But a main share is the electricity. And when we now go back to the slide of electricity footprint here, most of the battery cells today are produced in China and imported from China. So when you buy a BMW or a Volkswagen or Mercedes, there is a high probability that the battery cells come from China. And what we see here, we have a high impact electricity in China. That's the problem. When we can reduce the CO2 impact, for example, to European mix, so we produce the cells in Europe and not in China, we can reduce that to a half only by changing the electricity mix. So electricity production has a main impact also on the production of electric cars. Yeah, so far this was the production. Now about the usage. So when we use the car, we have a certain energy consumption for driving. Of course, this depends. So for this compact car, in average, it was 16 kilowatt hours. Larger cars, SUVs, can reach 20, 25. I tested the Audi e-tron last week. We had 30 kilowatt hours energy use on a highway. So it depends a lot. Then we have auxiliary devices. This is, for example, heating in winter times, so heating the passenger cabin, or the light or hi-fi equipment and others. It's about 10%. And we have charging losses. I just want to point out the charging losses because they are often neglected. So for low power charging, we have about 95 to 98% efficiency. So for low power charging at a wall box overnight, you have very high efficiency, low losses. But for high power charging at a supercharger, we have efficiency of about 80 to 85%, perhaps 90%, so something like that. What does it mean? The higher the charging power, the higher the losses during charging. And in that way, you have to consider that at a supercharger, it's more expensive, the charging, and the losses are also higher. What we have taken here is just an average number. I think we took about a little bit more than 15% or something like that in average. Yeah, and what we've done next is now to calculate the entire life cycle of different cars. So we had here a car with combustion engine. By the way, it was a BMW 1 Series with gasoline engine, 90 kilowatt, a standard compact mode car. We had a hybrid car. It was a Prius, so Toyota Prius hybrid, and electric car. It was the Volkswagen ID.3 as shown before. And we calculated both. We calculated the production CO2 impact and the usage. In the production of that car, we had 7.5 tons for the car with combustion engine, 9 tons CO2 for the car with hybrid drive, and 14 tons for the electric car I showed you before. The car with combustion engine has a fuel consumption of 6 liter, the hybrid 4.5 liter, and the electric car 20 kilowatt hours per 100 kilometer. When we put that results now in a diagram where we have the CO2 equivalent emission in tons over a certain driving distance, and we assume 200,000 kilometers, then we see here, this is the 7.5 tons of production of the car with combustion engine. And due to the fuel consumption over driving, it ends up with 40 tons over 200,000 kilometers. Also included here is maintenance and service, but the impact of that is very small. When we take the hybrid, we have here the 9.5 tons in production. We have a lower fuel consumption, so 4.5 liter per 100 kilometer, resulting in 33 tons in total CO2 emissions. For the electric car, it depends a lot how electricity is produced, right? So we have here the 14 tons of production, that's clear. And then it differences. So when we use the car in Norway with hydro power, electric power, we have a very small electric or CO2 footprint of 16 tons. But when we drive the electric car in Poland with a high share of coal power, it's even worse than the combustion engine car. So in that way, it depends on how electricity is produced. This is the main factor. I have just here some examples. This is the European average 26 tons which is, of course, significantly lower than the 40 tons of the car with combustion engine, right? But we can calculate now some our break-even point. So when we look at comparing the car with combustion engine and the electric car with low impact electricity, the break-even point is at 45,000 kilometers. So about three years usage, right? When we compare that with the European energy mix, we have 65,000 kilometers, or in Germany, 80,000. A little bit more tricky, for example, is to compare the hybrid, which is very efficient, in the German electricity mix. And here it's 120,000 kilometers for the break-even point. So here it's very late in the life cycle of the electric car. Yeah. So to summarize this, when looking at electric cars and also considering production of electric cars, the technology of electricity is the main important factor if electric cars are lower CO2 than combustion engines or not. Was there a question?
Yeah, I would like to ask you, it's only point of view of CO2 production and not about local emissions like nitrogen oxides and other small particles and so on. So it's usually talking or speaking in a public area only about the CO2 emission and global CO2 emission, not about the local CO2 emission, local exhalation in the cities, and impact to the health, for example.
Yes, absolutely right. So this comparison does not consider the harmful exhaust emissions.
Yeah.
So this comparison, of course, with combustion engine, I have harmful exhaust emissions, which also has a big impact on the air quality in cities, for example. But I did not show that in the diagram. So it's only CO2 what I was looking at. This is correct. Yes.
And Mario, do you have any materials, any information about the full impact of the different propulsion systems in all the emissions, harmful emissions, not only CO2, but also, for example, heat production or water production, because there was mentioned the water as an emission. What's the impact of the water production in a full cycle of the car? Is there any specialist who care about this or who speak about it?
There are impacts. So the water use is a factor in battery production, for example.
Yeah, but water is used as in a closed cycle. There is no production of water, but if you burn some carbon fuels, you produce additional water, which stay in the atmosphere and stay on the surface of the Earth and cannot be recycled or reused or returned back to the ground.
Yeah. So the water that is evaporated into the air by combustion engines is assimilating the weather cycle. So water does not remain in the air so long as CO2, for example, because it condenses and then it rains down.
Yeah, so, but in time between this evaporation and condensation, it takes some time, and during this time, it causes some greenhouse effect also.
Yeah, that's clear. This is correct. Yes. I did not consider in this study here I showed today, I only focus on CO2. But I agree with you, there are other effects. But in terms of, I go back to the harmful emissions. Let me see.
Yeah.
Here. This is something that we can reduce technically. So these harmful emissions, of course, they are bad for the environment, but we can lower these values by technical measures, exhaust gas after treatment. And today, these harmful emissions are a very small percentage. So in modern cars, in old cars not, but in modern cars, we can reduce them technically. But the CO2 emissions, here we only have limited possibility to reduce. In that way, the CO2 targets are seen as the highest challenge to reach. Also, I agree with the water that contributes to the greenhouse gas effect, and there are other gases like methane and others. But the CO2 is seen as a very relevant source that we have and that we should reduce. In my study, I show you today, I just have focused on CO2 emissions. But I agree, yes, there are also other gases.
Yeah, so we have about 10 minutes, I think, or 10
Yeah,
15
I have some more slides. If you agree, I would
Yeah.
like to talk about alternative fuels. I will do it very quickly if you agree. The one is hydrogen. What's about hydrogen? The advantage of hydrogen is that we don't have CO2, carbon inside, so it does not produce CO2. And hydrogen can be used in a closed cycle. So we can produce hydrogen out of water. We can store hydrogen in tanks. So these are typically 700 bar tanks, so very high pressure. And we can use them in combustion engines or in fuel cell systems to produce electrical and mechanical energy. And with this, we have a cycle process. This is the big advantage of hydrogen. But, and now comes the but, this only works when we use water as a source of hydrogen. Then we can do it. But today, about 95% of all hydrogen that we have on Earth is made from natural gas. Natural gas is mainly methane. It's CH4. I don't go to the time reasons, I don't go into detail too much, but we see here with CH4, we have a lot of hydrogen, right? And we can separate that very cheap, very easy from methane, but this produces CO2. So it's not CO2 neutral. And the biggest challenge that we have with all the hydrogen economy is to reduce that 95% to electrolytic hydrogen, so made of water. This is the main task. All the others, so we have applications in trucks, even cars, some of them, or other applications. This will work when we can establish a green hydrogen community. This is the most important factor here. Here I have just prepared some information about the hydrogen fuel cell vehicles. I will not go into detail due to time reason, but hydrogen is very expensive today. And it has a CO2 impact when it's made from natural gas. So we need to go to renewable or solar, wind energy to produce hydrogen to come to near zero. This is the hydrogen story. The another one is e-fuels. We have different types of chemical fuels. We can use biofuel. We talked about that. But today, much in discussion is the e-fuel. What is the idea? The idea is to take CO2 from the atmosphere here to use electric energy for a synthesis process of hydrogen plus CO2 to have then here hydrocarbons, so these are HXCYs, as I mentioned before, as e-fuel. And the idea is that here we take the CO2 from the atmosphere, we produce fuel, we use it to drive cars, and then we burn the fuel, and at the end, CO2 is released again, which also enables a cycle. In theory, it works, and there is also a prototype power station in South America, in Chile, but it's very expensive. So just to give you an idea, for 1 liter e-fuel, we need 3 liter water. We need about 6,000 cubic meter air for CO2 extraction and 16 kilowatt hour. I would say even a bit more. So it depends on the calculation. I would say 20 kilowatt hour about. And this results in 1 liter fuel with 8 kilowatt hour energy content. So we have a huge effort. We have efficiency of less than 50% because we need, or about 50%, we need 16 kilowatt hour electricity to have 8.5 kilowatt hour energy content, right? And this, of course, makes it very expensive, but in general, it works. And at the last slide, and this is my last slide of today, I would like to discuss the 3 technologies that we have available for driving cars and trucks for propulsion. The target is 0 CO2. And here we can use electric cars, battery electric vehicles, with green electricity, of course, so low CO2 impact electricity. We can use fuel cell electric vehicles with hydrogen, and the hydrogen also produced by green electricity, so not methane, green electricity. Or we can use internal combustion engine vehicles, and the e-fuels also produced with green electricity, right? So all 3 of them are more or less low carbon because the basis is green electricity or low carbon impact electricity. And what we compare here is well to tank, so preparation of energy or fuel, and tank to wheel efficiency. In case of the electric car, we have the electricity, green electricity, and we have some losses for transportation of electricity, right? So over distance. This leads to about 95% efficiency at the charging station. Then we have the charging station here. It's assumed with about 5% losses. It's very optimistic, but anyway, we have the battery charging losses about 5%. And then we have the inverter and the electric motor. I have to say, this is a bit optimistically. So I would say in real, we can reach about 65 to 77% total efficiency of this system. In case of hydrogen fuel cell, we have the green electricity and we produce the hydrogen. So here we have about 22% losses because of the electrolytic conversion. And then we have the storage. So we need 700 bar. We have to compress the hydrogen. And this also requires about 20% of energy content. So that in total, we have 61% well to tank efficiency. In the car, we have the fuel cell system, about 46% losses, and the electric motor and the inverter, so that in total we end up to about 30% total efficiency of the hydrogen powertrain. In case of the combustion engine, we have again renewable electricity. Then we produce the hydrogen. So this is hydrogen production, the same as here. And then we have this synthesis process, is a Fischer-Tropsch procedure to produce the e-fuel. So this is the, let's say, e-fuel. And we end up with a total efficiency of 44% because we need this high energy for producing of e-fuel. In the car, we fill it into the tank, and here we have the internal combustion engine with about 30% efficiency, so 70% losses, which ends up to about 13% total efficiency. What does it mean? We have the electric car with about double efficiency than the hydrogen car, and with a factor of about 5 of losses in terms of the car with combustion engine. So here we have factor 2, and here we have factor about 5. This means that we need 2 times more electric energy initially to drive a car with fuel cell, hydrogen fuel cell, and we need 5 times more electric energy to drive a car with e-fuels. That means for driving 100 kilometers, for example, the e-fuel will be 5 times more expensive than the electric car. In that way, the electric car will be the most suitable technology for many applications in the future because it will be cheaper to drive that. It's just a very simple estimation in terms of the efficiency of the system. Not considered in this slide is the storage of electric energy. This might be necessary to find technology to store renewable energy, wind energy, solar energy. So here this can change a bit, these values, but not a lot. The transportation is a factor, availability of e-fuels, for example, and of course, the infrastructure is also a factor not considered here. Yeah, with this, I would like to close my presentation. I hope it was something interesting for you and you enjoyed my talk today. Are there questions or discussions?
Yeah, absolutely. Thank you very much. Questions for student? Satisfied? Good. Everything is clear, probably.
That's fine.
Yeah,
thank you. I also have my email on the last slide of the presentation. So if you have questions, you also can drop me an email.
I have recorded the lesson and I will arrange with you how to share it between the students or public. So thank you for your attention actually now, and you can finish the lesson.
Okay, thank you very much and have a nice day. Bye-bye.